Hi, welcome back to my channel. My name is Gina. In this video, we're going to talk about the satellites. So in my video, when I talk about the weather forecast, I've mentioned that the satellites provide global measurements and help us to get a more accurate forecast. So in this video, we are going to talk about different types of satellites. So first, let's talk about different types of orbits. We can categorize them into 4 main groups. Panel A shows the equatorial orbit. It means that the satellite is orbiting above the equator, and the plane of the orbit is the same as that of equator. And then in panel B, there's the polar orbit. So this type of satellite will pass through the Arctic and the equator and then to Antarctica. And the plane of the orbit has 90 degrees inclination with respect to the plane of the equator. And then panel C and panel D show the oblique orbit, meaning that the inclination angle is neither 0 or 90 degrees. So here this image shows the proportional size of the Earth and distance to the satellites. So there are 2 main categories. There are this group of satellites that are further from Earth, and if that is the distance when people usually talk to other people, then the other group of satellites, they'll be like talking to your nose. So why are some satellites so far and why are some satellites that are close to the Earth's nose? So to understand that, we need to talk about some physics of the orbital motion. When an object is in a circular motion, it has a centrifugal force that is pulling the object inward. And the velocity v moves the satellite in one direction, and the acceleration a caused by the gravity changes that direction, and that makes the object orbits in circular motion. So the first physics concept, the force of gravity caused by a planet of mass capital M on a satellite of mass m depends on the radius of the orbit. And the radius of the orbit is from the center of the Earth to the satellite. And the formula for the gravitational force is the gravitational constant g times the mass of the planet and times the mass of the satellite, and over the radius of the orbit square. The second physics concept is the centripetal acceleration. So that is the acceleration that keeps the object in circular motion. And the formula for the centripetal acceleration is the tangential velocity v squared over the radius of the orbit. And then third, the time to complete the orbit or the period. Since the circumference of a circle is 2 pi r, so that will be the total distance to make one orbit. And time is distance over velocity. So the time to complete the orbit is 2 pi r, the total distance, over the velocity, v. Now let's combine these equations. From the first equation, we have the gravitational force equals to mass times acceleration, and that is Newton's second law. Then we can isolate for the acceleration and equate that to the second equation, v squared over r. And now we can isolate for the velocity, v, which equals to the square root of the gravitational constant times the mass of the planet over the radius of the orbit. And then we can substitute this velocity into the third equation, the period of the satellite. So we found that the period is 2 pi r over the velocity. Now we substitute the velocity, we get the period approximately equals to square root of r cubed over 1 times 10 to the power of 13. And just a quick note, when we say the radius of the orbit, it means from the center of the Earth to the satellite. But on Earth, we often say the distance to the satellite as the distance from the Earth's surface to the satellite. So here we defined h altitude as the radius of the orbit minus the radius of the Earth. First, let's talk about the satellites that are really close to the Earth's nose. So the ones that are really close to Earth. This type of satellites, they are in low Earth orbits. And there are many advantages using low Earth orbits. For example, if a satellite is closer to Earth, there's a better resolution. It's also easier to send some heavier satellites. But there are also some limits imposed by the atmospheric friction. So the low Earth orbiting satellites, they generally fly between 400 to 1,000 kilometers above the surface of the Earth. So on the right, you can see that there are different types of low Earth orbits. There are near polar orbiting satellites, and some of them are between 20 to 60 degrees of inclination. And if you want to observe the whole planet, you can use an orbit with a high inclination, because that type of satellite will fly from the Arctic to equator and then to the Antarctica. So as I mentioned before, the low Earth orbiting satellites are the ones that are really close to the Earth's surface. And on the right is an example of an image from the Terra satellite. And because the satellite is really close to the Earth's surface, so we can clearly see the structure of land, ocean, cloud, and lakes. As I mentioned before, if you want to have a global measurement, you can design the satellite to fly in near polar orbits. Because as the satellites orbit around the Earth is also rotating itself. So eventually the satellite can cover the whole Earth. For example, in this image, the first Earth shows the first orbit from the satellite. And at the same time, the Earth is orbiting to the right. So the second orbit, now the satellite is still flying in this direction. But since the Earth already rotates a little bit, so now the satellite will measure at a different geolocation on Earth. And same for the third orbit. Since now the Earth moved a little bit more, so the satellite will cover a different region on Earth. There's a special low Earth near polar orbit. It's called the Sun-synchronous orbit. Because the Earth is not spherical, so the gravity exerted on the satellite by the Earth does not exactly point toward the center of the Earth. And it will create a torque that will make the orbital plane itself rotate. So it's possible to design a satellite that has the same rotation rate as the rotating rate of the Earth around the Sun. So the Sun-synchronous orbits make the overpasses at the same time of the day all year long. Now let's talk about the other type of satellites that are further away from the Earth. They are called the geostationary orbit. And this type of satellites will look at a part of the Earth and it will follow this region on Earth all year long. So to make a satellite that observes the same part of the Earth, we need to make the period of the satellite the same as the Earth rotates on its axis. And it takes 1 day for the Earth to rotate once. So we want to make the period of the satellite the same, which is 23 hours, 56 minutes, and 4 seconds. And this type of satellites are on equatorial orbits. So from the previous slides, we've derived the period of the satellites, which approximately equals to the square root of the cube of the radius of the orbit over 1 times 10 to the power of 13. And we want to make this equals to 23 hours, 56 minutes, and 4 seconds, which is roughly 86,000 seconds. So now in this equation, the only unknown is the radius of the orbit. So we can isolate for that. And since the radius of the orbit includes the radius of the Earth, so we need to subtract the radius of the Earth from the radius of the orbit to get the distance from Earth's surface to the satellite. And that is roughly 35,000 kilometers, which is about 10% of the Earth-Moon distance. So it's because that we want to make them have the same period as the Earth rotation. So this type of satellites are further away. So there are many advantages using this type of satellites because if you are monitoring one part of the Earth all year long, then they allow us to frequently monitor the weather because it's staring at the same place. So we can use this type of satellites to study how a hurricane evolves, for example. On the lower right, there are a few examples of the satellites that are orbiting in geostationary orbits. And since the Earth is in spherical shape, so one geostationary orbit is not enough to monitor the entire Earth. We need about 5 to cover most of the Earth. Although this type of satellites are really useful as they help us to study the evolution of the weather events. However, there are two main disadvantages using the geostationary satellites. The first one, the paradox. Since the satellite is really far away from Earth, so when we look at the edge of the image, for example here, the satellite is here and is viewing this cloud. But because the satellite is really far, so we can misjudge the geolocation of this cloud. The apparent cloud position will be here, but the actual cloud position is here. The second disadvantage. So since the satellites are really far away from the Earth, so the resolution wouldn't be as good as those low Earth orbiting satellites. So just a quick summary of what we have covered in this video. So in this video, we've looked at the geostationary satellites and the low Earth orbiting satellites. The low Earth satellites have global coverage, especially the near polar orbiting satellites. And the low Earth orbiting satellites, because they are closer to the Earth, so they have better resolution than the geostationary satellites. As for the geostationary satellites, they observe events at any time. They are staring at part of the Earth all year round. However, the geostationary satellites can only cover about a quarter of the Earth, and we need around 5 satellites to get a global coverage. And the two disadvantages that we discussed are the parallax and resolution degradation. And finally, since the geostationary satellites are staring the same part of the Earth, so it has better time resolution. As for the low Earth orbiting satellites, it only passes the same area twice a day, once ascending and once descending. That is the end of the video. If you find this type of fun facts interesting, please comment below. And I'll see you in the next video. And that help us